Good morning, everyone, and welcome to Day 2 of the Inorganic Ventures 7th Annual ICP Conference. I'm Thomas Kozakowski, QC Manager here at IV, and I'll be moderating for you today. I hope you found yesterday's presentations to be helpful and informative for the work you do at your labs. Today's topics will expand beyond the basics covered in yesterday's session. A few housekeeping reminders for those of you with us live today. Please put your questions in the Q&A box at the bottom of your screen. We'll address these in our roundtable session at the end of today's presentations. Now I won't keep you waiting. Our first presentation will focus on ICP mass spec, planning for tough samples and problem elements by Dr. Brian Alexander. Dr. Alexander is an earth scientist specializing in geochemistry. His research has focused on radiogenic, isotope, and rare earth element studies of natural waters and chemical sediments, as well as trace metal analyses using ICP techniques. A native of Southwest Virginia, Brian received his BS in geology from Virginia Tech and his master's and Ph.D. in geochemistry from Penn State and Jacobs University Bremen, respectively. Brian currently serves as the Chief Technical Officer at Inorganic Ventures. I will now turn it over to Brian.
Thank you, Thomas. For the next 25 to 30 minutes, we want to focus on some of the basics of sample preparation. This is a very broad topic. There's quite a bit of information available in the literature regarding different sample preparation approaches. And so this presentation is intended to be a reference guide for your future use. It contains a great deal of information, most of which we will not have time to cover today in detail. So the approach that we're going to follow is to highlight those points that I feel are most important and give you a broad overview. The discussion topics are going to include some of the questions that you should ask when developing a sample preparation approach. We also want to look at element and matrix compatibility. If you are able to get your sample into solution for an ICP analysis, that's great, but we want to make sure that your final diluent, the matrix in which you are going to run your samples, is actually going to be compatible for your elements of interest. We also want to look at container material properties. What do you have in your lab that is available for you to use, and what concerns might you have regarding things like contamination risk? And then we're going to focus on three broad sample digestion techniques: acid digestion, fusion, and ashing. So when you are deciding upon a sample preparation approach, there are some basic considerations, and there are 7 questions that we feel are fundamental that you should ask yourself when picking a particular method. 2 things that I want to point out would be one related to the concentration range of the analytes and the detection limits requirements that you may have. One example would be you are asked to measure calcium and lanthanum in limestone. How do you calculate your detection limits? These 2 elements are present at very different concentrations in this particular sample type. Calcium will be present at thousands of times higher concentrations than lanthanum. Your detection limit is a function of your dilution factor. So it's possible for an ICP analysis, you'll actually have to do multiple measurements at different dilution factors, and you're going to have different detection limits as a result. Another thing that we want to think about perhaps is the stability of the analytes after sample preparation. What if you are asked to measure part per billion levels of gold and the sample matrix needs to be nitric acid? Will the gold be stable? This is something that you should be thinking about before you even begin the sample preparation approach that you will follow. And there are some other questions here that we really encourage you to be thinking about as you're designing your particular approach. So we're going to start off with the element and matrix compatibility, and we're going to focus on one of the most popular acids used for ICP analyses and sample preparation, and that's going to be nitric acid. In this and the subsequent slides, we're going to look at different acids. The key thing to think about is that every element that is colored on the slide has some type of compatibility with nitric acid. However, there are some caveats and things that you need to be thinking of. The elements that are highlighted in red are perfectly compatible in nitric acid, meaning that you will not form any nitrate salts or precipitates. The other nice thing is that these particular elements are perfectly stable in nitric acid, and this is a key distinction. It's one thing for an element to be compatible in the acid, meaning that you're not going to form a salt or a precipitate. It's another thing to ask the question of how long will that element actually be stable. There are a handful of elements that are compatible in nitric acid, but require some type of complexing agent to remain stable for an extended period of time. Some of the ones that are highlighted here are what we would call the HF elements, such as titanium, zirconium, tantalum, tungsten, etc. Each of these elements is compatible in nitric acid, but their long-term stability will be enhanced if you're able to complex them with something like a fluoride ion. Other elements that you want to be thinking about that are compatible with nitric but need some type of complexing capability would include the precious metals, such as ruthenium, platinum, or gold. One element that we absolutely encourage you to avoid using nitric acid matrices for would be osmium. Osmium in an oxidizing nitric acid matrix can form the tetroxide, which is volatile and quite deadly. So of all the elements on the periodic table, you can use nitric acid with the exception of osmium. For some of the other elements though, such as the HF elements or the precious metals, you'll want to consider the addition of some complexing agent such as fluoride or chloride. Another very popular acid for ICP analyses and sample preparation would be hydrochloric acid. Hydrochloric acid actually is more compatible with more elements on the periodic table than nitric acid. And however, like nitric acid, there are a few elements that will benefit from the addition of some complexing agent such as fluoride. So these again will be the HF elements previously mentioned, such as titanium, tungsten, also including tin, germanium, or silicon. For those elements, they're perfectly happy in hydrochloric acid, but the long-term stability will be enhanced with the addition of a complexing agent like fluoride. The one element that you really want to avoid in a hydrochloric acid matrix would be silver, which will form the well-known silver chloride complex as a precipitate. However, if the concentration of silver is low enough and the concentration of HCl high enough, then you actually can form a stable solution. And the rule of thumb we use at IV is roughly 10 parts per million of silver is perfectly stable and roughly 10% volume dilution of concentrated hydrochloric acid. So if you follow that rule of thumb, you should be able to keep your silver perfectly happy and stable in hydrochloric acid. Another element that's commonly used in sample preparation will be sulfuric acid. Similar to hydrochloric acid, many elements, if not most of the periodic table is compatible with sulfuric acid. A couple of notable exceptions would include things like strontium, barium, or lead. And some of the previously mentioned elements will also benefit from an additional complexing anion, such as fluoride or chloride. But most of the periodic table really is just perfectly compatible with sulfuric acid, as we've seen also with nitric and hydrochloric acid. The last acid we want to look at would be hydrofluoric acid. And this is an acid that many of you might not be able to use in your lab. There are fewer elements that are compatible with HF compared to the previous acids we've looked at. These are primarily going to be the alkaline and the alkaline earth elements, as long as the rare earth elements. Other than that, really you only need to worry about barium and chromium as not being compatible or stable with HF. However, those concentrations need to be relatively high, say 500 ppm in the final solution. One thing to note is even though all of the acids we've looked at do show some type of compatibility or stability issues for some elements, a key thing to remember is this: as the concentrations in your solution get lower and lower, pretty much the entire periodic table will be stable in any number of these acids in a range of acid concentrations. So the take-home message would be this: if you keep the concentrations low, a lot of the stability and compatibility issues we've looked at will go away. And the concentration range you might want to keep in the back of your mind is about 1 part per million. If you're below that in your working solutions, almost every element will be tolerable of essentially every acid that we've discussed here. Next, we want to look at some of the material properties that you might be encountering in your lab. Common materials that people use for sample preparation include glass, porcelain, quartz, platinum, graphite, or plastics, which tend to be the most popular. And we're going to look at some of the considerations that you should think of when using any of these materials in your lab. First, for borosilicate glass. It's used very extensively. It has excellent resistance to most acids. We want to avoid HF, however, or boiling phosphoric acid. And as a general rule, alkaline solutions should not be heated or stored in borosilicate glass. It can introduce a variety of contaminants. The table here shows some of the contaminants that are easily leachable from borosilicate glass. Many people might think that silicon would dominate, but it's actually calcium. So if you're doing trace analyses and you're using borosilicate glass and any of the elements you see here are part of your analyte panel, you really want to think about, are you adding some type of contamination because you're using borosilicate glass? The last point is just that borosilicate glass should not be heated above about 500 degrees C. And we'll see why the next material is actually more advantageous at higher temperatures. And that material will be porcelain. It's a very popular material used for ashing purposes, and we'll talk a little bit more about that later. It does contain significant amounts of sodium, potassium, aluminum, and silicon in increasing concentration. What's important to remember about porcelain is that attack of the porcelain crucible will occur if the sample contains even minor amounts of the alkali metals. And you'll see this because the surface will become increasingly more dull over time and as you use it. The biggest advantage of porcelain over borosilicate glass is its temperature resistance. It can be heated to 1100 degrees C, and this higher temperature resistance is particularly useful for some of the later methods that we'll see, such as fusions and or ashing. Another common material found in the lab would be quartz. There are two basic types of quartz available, opaque and transparent. The transparent quartz comes in a number of different varieties, and additional information is provided here. The key takeaway would be that you really want to use the type 3 quartz wherever possible. Similar to porcelain, quartz will be attacked by HF, boiling phosphoric acid, and the alkali and alkaline earth oxides, hydroxides, and carbonates. Similar to porcelain, it can be heated to 1100 degrees C. And the biggest advantage over porcelain, however, is that the major contamination from quartz is only going to be for silicon. So that is the big advantage of choosing quartz over porcelain as a container material for any of your sample preparation approaches. One very excellent material for sample preparation would be platinum. Its advantages include it's resistant to most acids and reagents. Similar to the borosilicate glass and the porcelain, we want to avoid concentrated phosphoric acid at high temperatures. You also want to avoid aqua regia mixtures in any fusion that's using a lithium carbonate or an alkali peroxide. The platinum that you are using can be destroyed also by heating with metals with which it can alloy. So you really want to avoid high temperature heating of your platinum crucibles with any samples that contain significant levels of metals that could be reduced. So you're thinking of things like the precious metals, copper, and or mercury. So platinum is really an excellent container material. It is expensive, but if you follow some of the guidelines here, it should last you for many, many years. Another material that maybe is not used quite as frequently is graphite. Some of the advantages of graphite are that it's very inexpensive and it's relatively clean, but it is messy to work with. One of the primary uses is that it is a very inexpensive way to perform lithium carbonate fusions, where the crucible slowly oxidizes away over a number of fusions and then you simply discard it. The biggest advantage of graphite is that it can withstand fusions that might destroy your platinum. So if you're a little bit unsure and you don't want to risk your platinum, you can use a graphite material and kind of test drive the sample preparation before moving on to your platinum and taking any risks. Plastics is probably the most common and preferred material for a number of sample preparation methods. So here we're going to list some of the physical properties of common plastics. These are mainly going to be a range of fluorinated plastics or Teflons, and also include things like polypropylene or high and low density polyethylene. So while some of these physical properties are not terribly attractive, say for the polyethylenes because of their temperature restrictions, we'll see in the next slide that some of these plastics are really fantastic, not only because they're cheap, but because they're cleaner than some of the materials that can withstand much higher temperatures. And so what we see here is an impurity analysis of the different types of plastics we saw in the previous slide. We have the total part per billion impurities in a leaching solution as part of the y-axis, and then the plastics themselves are designated on the x-axis. What we have found, and these are data that we've generated in our own lab, is that low-density polyethylene is by far the cleanest plastic that you can use in a sample preparation. The big advantage also is that it's incredibly cheap. So if you can avoid high temperatures, low-density polyethylene is really the preferred plastic for any type of sample preparation, but also storage of your solutions. It really is super clean, and it has a lot of great properties with regard to the contamination risk. So we've talked about the questions that you should be asking. We've talked about some of the container material properties and the element and matrix compatibility of your final solutions. Now we want to focus on the three big groups of sample preparations: acid digestion, fusions, and ashing. And starting off with acid digestion, acid digestions can retain volatile analytes, though you'll have to have some special equipment perhaps for that. If you have a microwave, that's fantastic. You can avoid some of those problems. The big thing to take away for acid digestions is that it really is going to be an ideal approach if you can keep the sample size small. We don't recommend doing acid digestions on 2, 3, 5, 10 gram samples, and some of the other approaches we'll look at will be helpful in actually reducing that sample size. Nitric acid is a very popular acid digestion acid because of its chemical compatibility, oxidizing ability, and low cost. So we're going to focus on HNO3 first. It's a useful component for the destruction of organics, but nitric cannot by itself completely decompose organic matrices. So here we have some additional information for all the different sample types that you can attack with nitric acid. And the one that I highlight at the bottom of the slide is a very powerful one, where you're using a combination of nitric, HF, and water. This is really, really good for a number of refractory oxides and alloy mixtures containing one or more of these elements. You don't necessarily have to use quite that much HF. You can use probably a smaller amount depending on what you're trying to measure, but this is a general recipe that is very effective for a number of difficult samples. Continuing with nitric acid, one of the key benefits of nitric is that it does not form any insoluble compounds, unlike sulfuric, phosphoric, perchloric, etc. One of the key things to remember is that nitrate is a poor ligand. It doesn't have the coordination ability to keep hydrolysis from occurring for some elements. And if it was a better ligand, then you wouldn't have to use other acids. But most commonly, you're going to combine it with things like HCl, HF, or tartaric acid. And if nitrate were simply a better ligand, those additional acids would not be needed. Sulfuric acid is similar to nitric in that as a dilute acid it has no oxidizing power, but hot concentrated sulfuric does. One very powerful approach is to use the dropwise addition of 30% hydrogen peroxide in addition to your hot fuming sulfuric acid to decompose organic matrices. You can also mix it with things such as nitric and HCl for steel samples, and if you mix it with nitric and perchloric acid, it's very powerful for hard to oxidize organic samples. So we want to take a moment and focus on the use of nitric acid for organic samples. Nitric acid can react with alcohols and aromatic rings to form explosive compounds, and therefore the use of nitric acid for the digestion of highly aromatic samples is not recommended. If your sample contains hydroxyl functionality, it's best to pre-treat the sample with concentrated sulfuric acid. And again, we really want to remember that nitric acid by itself, even in concentrated form, is not capable of breaking down organic components strictly to carbon dioxide and water. If you're using nitric for organic samples, you're probably not going to want to use it alone. It's best used in combination with some of the other mineral acids that we've talked about. And one good approach for samples that are not highly aromatic or that do not contain hydroxyl functionality is to use nitric acid followed by perchloric acid. Really, the only element that's going to be lost from this particular approach would be mercury. Again, we would just say exercise some care and consult the literature before attempting to use nitric acid in combination with other acids for organic sample digestions. So just a few closing remarks on organic samples and the use of nitric and perchloric acid. Perchloric acid should never be used alone. Perchloric acid digestions should not be allowed to go to dryness. Never add hot perchloric acid directly to an organic matrix, and please keep your sample sizes small, less than 1 gram. Lastly, you should not be using perchloric acid unless your lab has a specially designed hood that is compatible with perchloric acid digestions. Next, we're going to move on to fusions. For trace analyses in particular, fusions should be considered a last resort. Some of the things that you should be thinking about are that large dilutions of your sample are going to be necessary. The flux that you're using in a fusion will be present at, say, 7, 10, or 20 times the mass of your sample. So large dilutions are going to be appropriate to avoid things like salting out in your nebulizer. You really want to be thinking about spectral interferences from either the flux or the crucible construction material. And in spite of all these considerations, there are going to be times where fusion is really the best or the only option for your sample preparation. The first one we're going to look at is pyrosulfate or bisulfate fusion. This is really good for refractory oxides such as titanium, niobium, or tantalum. One thing to do or to think about when you're performing this particular type of fusion is that you can regenerate the flux by adding sulfuric acid dropwise. And so if you see that it's not going quite the way you would like and the flux is beginning to solidify, just add some sulfuric and you'll regenerate that flux. If you continue on with this particular fusion, the one thing that we would ask you to think about is that you really would want to think about this when dealing with refractory oxides. These refractory oxides are typically going to form when your ignition ashing temperature is too high. We'll talk a little bit more about that. But if you've got something that won't go into solution, this is a good approach. Lithium borate is another popular fusion. This is a really good one for aluminosilicates and various mineral types. A lot of these lithium approaches have been automated, which is fantastic. And the nice thing is that when you're done with the fusion, you can just dilute the fusiate in 5% nitric acid. And this is a very common approach. It's a kind of a one size fits all for a lot of different materials, and it's very commonly used. There are also hydroxide fusions, such as sodium or potassium hydroxide. The big advantage of this approach over a borate or carbonate fusion is that you can use a much lower temperature. You want to avoid using platinum for this because of attacking of your crucible, and the crucible choices are typically going to be silver or nickel. Again, the big advantage is it's just going to be that you can use a lower temperature, and you need to be aware that you can have greater crucible attack at higher temperatures. You can also use a potassium hydroxide in combination with a nitrate. This is really a good approach for things such as ruthenium alloys or samples, organics such as biomaterials or soils, and you're going to want to stick to a silver crucible for this one. Similar to the previous approach, you will have greater attack at higher temperatures, so make sure that you are able to control your temperatures very, very well. This is something that is, in our opinion, in many ways the best all-around approach for a fusion. It's a sodium carbonate fusion. It is really good if you're not quite sure what's in the sample and you just need something that you think is going to apply to the widest range of sample types. So this is something that we're big fans of. We would recommend using a platinum crucible. It's pretty quick and it can really attack and decompose a wide range of sample types. Lithium carbonate is very, very popular as well. The biggest advantage is that you can use it at a lower temperature than the sodium carbonate approach, but the big disadvantage is you cannot use platinum. Some of the other advantages are listed below, including some things that you should be thinking about whether you're an ICP OES user or an ICP MS user. Now, the last thing that we really want to look at would be dry ashing or ashing techniques in general. So this is where you're going to take your sample and you're essentially going to combust it and try to destroy combustible organic portions of the sample. So we're going to start off with what's known as a dry ash, and you're going to use any number of containers. You could use a platinum crucible or a porcelain crucible. You want to keep your ashing temperatures low. If you get above about 500 degrees C for any of these ashing approaches, you can start to form some of these refractory oxides, which can create problems for getting everything into solution. Commonly, magnesium nitrate will be used as an ashing aid. It will help with the oxidative approach for these ashing methods, and it also can assist with things like the friability or ashing losses during the insertion into a muffle furnace. You can take dry ashing a little bit further and you can do what's known as a sulfated ashing. This is where you add small quantities of sulfuric acid after you've charred the sample. And regardless of the ashing approach, the typical idea would be this. You're going to char the sample first on a hot plate, and then you're going to finish the ashing in a muffle oven. For sulfated ashing, what you're going to do is you're going to char the sample, then add a few drops of sulfuric acid. It's really helpful for preventing the volatilization loss of chlorides, but you really want to think about does your sample contain barium or lead? If it does, and these are analytes that you're concerned about, you want to avoid the addition of sulfuric acid. You can do wet ashing with sulfuric acid. What this is going to involve is that you're going to actually add the sulfuric acid before you char the sample on a hot plate. And the big advantage is you're going to choose this approach because it will help avoid crucible attack with caustic samples or analyte loss through reaction with the crucible container. There is something known as low temperature ashing. This is very good if you need to measure volatile analytes such as arsenic, antimony, etc. It also virtually eliminates the reaction between sample and ashing container. However, it is slow, and it's not going to therefore be very advantageous if you have a high sample throughput that you need to achieve. Closed container ashing, this is most commonly going to be used for halogens and elements such as phosphorus or sulfur. It involves a thermal decomposition in oxygen in a closed system such as a Schoeneger flask. It's widely going to be used in microelemental analysis, but unless you're concerned about a volatile element or a halogen, you're probably not going to be focused on this particular approach. So what are some of the pros and cons of ashing? The big advantages of ashing include the ability to decompose large sample sizes. So if you think back to where you want to keep your sample size less than 1 gram for some of the acid decomposition methods, you can do an ashing approach first, decompose some of the organics, and then move on to something like a acid digestion to get your sample into solution. You also really don't need any reagents for an ashing approach. The big disadvantages are going to be possible loss of analytes due to retention on the ashing container, also the loss due to volatilization. Contamination from the ashing container or the muffle furnace are things that you really want to think about as well. So, some of the problems and ways to avoid them when it comes to ashing. Please protect your platinum. It's an investment, and so you want to avoid things like phosphorus, copper, mercury, or the precious metals. For difficult to dissolve oxides, you want to use a low ashing temperature. If you really get much above 500 to 550 degrees Celsius, you will start to convert some of these metals, particularly things like chromium, into very refractory forms. And at that point, it's going to be difficult to get them into solution unless you go with some approach such as a fusion. And always be aware that trace amounts of your crucible material will contaminate the sample solution. So that wraps up this sample preparation presentation. A lot of information. If you have any questions, please reach out to us, whether during today's presentations or at a later date, and we'll be happy to help you with those. Thank you.